joining joining us today for the second day of 2 days free workshop on enhanced oil recovery, fundamentals, screening, and the role of simulation, instructed by Mr. Ishmael Ibrahim, who is a senior reservoir engineer having around 39 years of wide experience in oil and gas industry. So without any further delay, I would like Mr. Ishmael sir to continue the session. Thank you, sir. Over to you. You can start now.
Good afternoon, everybody. We are today, I think, Jata, we agreed yesterday that to make it for 2 hours for today in order to complete everything and close the workshop. Yeah?
Yes, sir. Yes, sir.
So we will have 2 hours today. We will start with the first one now. And then we will take about 15 minutes, just a refreshment between the two sessions. Then we will continue to finalize the this one, and so please keep your questions till the end of the second session in order that I can answer all your questions and can have time, because the second one is not so long, so we will have time. So please make your notes, and then we will talk about this later on. And first, today is the continuation of yesterday, and today session I will answer some of your the questions that were ambiguous maybe to somebody. And today we will start with the miscible gas flooding hydrocarbon injection highlights. In this process, we will inject hydrocarbon gas to light the hydrocarbons through the reservoir to form a miscible fluid. The mechanism that improve recovery efficiency, that we will reduce viscosity, increase oil swelling, condensing or vaporizing gas drive. That means we will enhance here the gas drive of the reservoir. So this is a diagram of the surface facilities and the downhole operation that will take place in case of using this kind of miscible flooding. First, you will see that number 2 is the oil bank, which is a miscible front. This oil mixed with the hydrocarbon gas injected into the injection well, and then we follow by hydrocarbon and water zone, then followed by drive water. In this case, also in order to push the hydrocarbon gas to be miscible with the oil and the reservoir. And then the fourth one, this is to push the whole mixture to the producing well and produce this hydrocarbon. Miscible gas flooding limitations that we have. It is used for minimum depth and the pressure needed to maintain the generated miscibility also. The required pressure range from about 1,200 psi for the LPG process to 3,000, 5,000 psi for the high pressure gas drive, depending on the oil characteristics or properties present in the reservoir. The challenges here we have here viscous fingering results in poor vertical and horizontal sweep efficiency. During this operation, a viscous fingering will happen or may happen, and then we will produce the gas earlier than is expected. So in this case, we will decrease the efficiency of the vertical and horizontal sweep efficiency. Large quantities of expensive products are required. Solvent may be trapped and not recovered. Sometimes the solvent that we inject with the gas, hydrocarbon gas, will stay in the reservoir and will be trapped. So in this case, we will lose the solvent because on the surface, the separation will be done on the mixture in order that to separate the oil from the solvent and the gas that's injected. But so in order to use it again in the next stage or at the same stage, but this kind of miscible flooding may leave the solvent may be trapped down there in the reservoir. Thermal flooding. Thermal flooding is a steam flooding consists of injecting about 80% quality steam to displace oil. This is here comes the answer of some of the attendants about the thermal flooding. Normal practice is to proceed and accompany the steam drive by a cyclic steam stimulation of the producing well, which is called huff and puff. The same producing well, we use it first. We inject about 80% steam quality. Wait for some time. That will take maybe 2 or 3 days. What will happen down there? The steam will soak the residual oil or the leftover oil. Then after that we will open the same well where we injected the steam to produce what's can be produced from the hydrocarbon left down there. Well, this operation is called huff and puff. That's at the same well we use it huff to push inject steam, and the same well is open to production. This is the puff that will produce what the steam can cover, and down there what will happen, that's the steam will come back to be, when it is cooled down, it will come back as water, and then this water is still hot, will decrease the viscosity of the oil and act at the same time as a drive to push the hydrocarbon back to the producing well. Also, mechanisms that improve recovery efficiency. That's here in this case, so this process, we used the steam, and then we will improve the mechanism of the reservoir by first viscosity reduction and steam distillation, thermal expansion. When the steam comes in contact with the oil, there will be an expansion of the oil down there, and this will aid in pushing the hydrocarbon to be produced with less viscosity and with more expansion of the quantity of oil. Also supplies pressure to drive oil to the producing well. As I said, when there is thermal steam down there, when it cools down, it will become it will act in two ways. The first way, since it is hot, it will push expand the oil and push it to the producing well, and at the same time, when it cools down to and condensate then this steam will becomes water. Will push the hydrocarbon to the producing well. This is a diagram, shows the operation that happens down in the reservoir, and at the same time show you the facilities that's required for this operation. Here we will need a steam generator. If you look to the screen, you can find it on the left side of the screen. And then we inject this steam into the well. The steam and condensed water will push the oil, hot water and oil bank will happen. and then oil and water zone near original reservoir temperature. And then this expand the oil and push it to the producing well. When it's produced, then we will take it to the separators and storage tanks. But limitations of this process is that it's applicable to viscous oil in massive. That's you have to have a massive quantity of hydrocarbon, and this one should this process will act on this quantity by decreasing the viscosity of the water of the oil. And also you should have high permeability sandstone or unconsolidated sand. It will be better for the operation. But then you will have oil saturations must be high. You should have high saturations of oil. Phase zone should be greater than 20 feet thick to minimize heat losses to adjacent formations. A steam flooded reservoir should be as shallow as possible because of excessive wellbore heat loss. I would like to mention some point here. All these operations will be shortlisted, and you will have tables that show you how to use it, what to use it, and what are the limitations of these processes by near the end of the course. So in this case, we will have thermal steam acting on reducing the viscosity of the oil and expand the quantity of the oil, and then this will then we will have two driving mechanisms. One of them is the first one is the expansion of oil, and the second one reduction of viscosity. All this will share the production of the hydrocarbon. We may have more limitations on this process. The steam flooding is not normally done in carbonate reservoirs. You cannot use it. Since about 1/3 of the additional oil recovered is consumed to generate the required steam, the cost per incremental barrel of oil is high in this case. A low percentage of water-sensitive clays is desired for good injectivity. What water-sensitive clay this will aid in keeping the water and keeping the that comes from condensing the steam. This condensation will produce, of course, as I said, the water, which will be kept by the clays as water in the reservoir, which aids in pushing the hydrocarbon. The challenges that we have in this process is that adverse mobility ratio and channeling of steam. You may have channeling of steam. That steam will be produced before producing the oil if some of the properties of the reservoir are not met. Then we come to the point that which EOR methods is required. What else? What we need from in order to choose the best and the suitable EOR method? We need reservoir performance and well performance. These can be obtained by reservoir simulation. Here comes the role of the simulation. The performance of the reservoir and the well will show you that after several years of production by natural driving mechanisms, you will have will show you that your reservoir is not producing as required, or even the water oil ratio increase. Then you will have reduction in pressure. In this case, you can decide at what stage or what time you should use EOR. This can be done by implementing the reservoir simulation. So let's go and see what kind of information needed. What is the simulator? What are the... So let's go and see. Reservoir simulation introduction. Sorry. Why we simulate a reservoir? Methods for handling uncertainty have become increasingly used to aid companies in spending limited budget on the best opportunities in their portfolio for field and prospect. This will give you a shorter way to decide and to use the AOR or implement an AOR method. This can be done by the simulator. And the simulator will show you the shortcuts where and when to use the recovery or AOR process. What is simulator? What is reservoir simulation? Reservoir simulation is the representation of petroleum reservoir performance using a model. As you can see, this is a reservoir. There's the red areas are the where the concentration of the carbonate are higher than the blue, rather than yellow, and higher than the green ones. So the reduction in concentration comes from red, yellow, and the green. Then on the base, you will see that's blue colors, which means that's water areas of the water area of the reservoir. What is reservoir simulation? It is a form of numerical modeling that you model your reservoir by using numerical processes, which is offered by the simulator, to model your reservoir and see what kind of reservoir you have down there. Used to quantify and interpret physical phenomena with the ability to extend these to project future performance. The process involves dividing the reservoir into several discrete units in 3 dimensions. You will see here your reservoir in 3 dimensions. You can turn over up and down, left, right, and you can see what is the shape of your reservoir you have down there. Modeling the progression of reservoir and fluid properties through space and time in discrete time steps. Also, you can see the change of the fluid properties and the progression of the reservoir at the same time in different time steps, and you can choose within months, within days, you can see what kind of changes that will happen on your reservoir during the production life of it. Reservoir simulation. Typical uses of reservoir simulation includes assess, valuation, or accurate determination of recoverable reserves. They show you the accurate determination of recoverable reserves, and you can have also you can asset management, which means the hydrocarbon quantity on and how to use it, and in what position and in what situation, and where to produce more, where to produce less. Determine the most economical perforation method, where to perforate. To show you the well pattern used to injection or production, as we said, that's either 5-spot or 7-spot production. Number of wells to drill and rates, also can show you the number of wells and the number and the rates of each well. Determine the appropriate facilities, what kind of facilities you should have on the surface, and what kind of facilities you have downhole and down there in the well. Typical uses of reservoir simulation includes uncertainty management. Uncertainty management, you always have during the simulation and during the life of the or during in any reservoir, you have certain certainties. You may have change in facies, change in feed of the water zone, or change in the energy of the reservoir. So the simulation can show you these uncertainties. So it is you can estimate financial risk of exploration prospects and early life cycle fields. You can assess of early gas or water breakthrough or coning. Also, you have here breakthrough and coning during the production life of the reservoir. Estimate means of meeting gas deliverability contracts. Are you meeting the contract or not? The simulation will show you. Many government agencies require simulation prior to approval of secondary or tertiary optimization programs in order that to be sure that you are investing your money in a well in a in let's say in a good situation, in a good reservoir, and then you have to have approval that you are investing well in this reservoir. When you should use reservoir simulation? When the problem cannot be solved by any other way, mathematical and ways to can solve it or change they change the downhole equipment. The simulator will show you this. When reservoir simulation is faster, cheaper, or more reliable than other methods, it will give you a faster and cheaper way of seeing what's going down there. But a general rule, problems should be solved using the simplest and least costly method that will yield an answer consistent with the objective of your study and the available data. Of course, the results will depend on the available data and its quality. You should have a higher as possible quality of information fed to the program in order that to give you the right answers and the suitable answer. Also, less costly. So the mathematical representation of the reservoir can range from a very simple model, the tank type, or zero-dimensional model, to a highly complex set of equations that require numerical techniques and computers for their solution. The reservoir simulation approach, this is called. So you can simulate a very simple model, and you can simulate also a complex one. Reservoir simulators. Commercial black oil and compositional simulators are formulated to model up to 3 phases: oil, gas, and water. Some simulators include gas in the water phase. The ability that's gas dissolved in the water phase. The ability to model gas solubility in water is useful for applications such as CO2 flooding, coal gas production, and production from geopressured gas water reservoirs. Usually, in the geopressured reservoirs, we have gas dissolved in the water. So you should have a simulator that can show you what is your how to implement the EOR and how to implement the kind of production that you are required to do it. Some simulators include condensate as we all know that when we can have condensate with the gas produced from if the reservoir is gas field or gas reservoir, you may have condensate coming down out uh, with the gas produced. Simulators must include what you should have in the simulator, or this will aid you in choosing the best simulator for your case. Simulators must include reservoir structure, can show you the reservoir structure, a fluid PVT, rate equations for modeling wells, phase potential calculations, relative permeability and capillary pressure curves. Can do all the simulator should have all these 5 categories in it, and it is, you can say this is the best one. Saturation dependent rock fluid interaction data entered either in tabulated or analytical form. This is quite clear, I think, for you, because you should have fed the data, available data, in the tabulated or in any other way that you may use in EOS. That's the equation of a state, in order that you can simulate that if you don't have a quite good PVT sample, you can simulate the type of sample that's the type of PVT that you're going to use in this reservoir. For example, in Eclipse, referred as E100, which is the simplest one, black oil simulator. It assumes that oil and gas phases can each be represented as one component through time. The properties of this component can change with the pressure and temperature. The composition does not change with pressure and temperature. Black oil simulators include oil and gas phases represented by one component, and assumes the composition of oil and gas components are constant relative to pressure and time. The compositional simulators in Eclipse, for example, I'm taking here Eclipse example, and you may have some other simulators, we will show it later. The compositional simulator in Eclipse referred as E300. It tracks each component of the oil and gas in the reservoir, C1, C2, and etc. It is used to model fluids near the critical point, where changes in the pressure and temperature can result in very different fluid behavior. Of course, as you know, the any fluids in the reservoir will change its behavior according to pressure and temperature, which is referred here to the gas mainly, and when to become gas, when it's fluid, or when it is fluid, and when to become gas again, or condensate, where to find it. And this is called the phase behavior. Oil and gas phases are represented by multi-component mixtures. The compositional model assumes the reservoir fluids are at all temperature and pressure. Composition and time can be represented by equation of a state. Here it comes to equation of a state that can simulate for you the type of fluid you are going to have in the reservoir. A thermal recovery simulation equation and model. The energy balance equation contains non-linear terms. Energy loss to adjacent non-reservoir rocks must be computed. The resulting complexity requires substantial computation to achieve energy balance. Reservoir temperature variation is light and the energy balance equation can be neglected. This is substituted by imposing the isothermal approximation, the K factor, if you all may know. This approximation results in substantial reduction in computation expenses with a slight loss of accuracy. Why I mentioned here the thermal recovery simulation equations and model, because this approximation results in substantial reduction in computation expenses with a slight loss of accuracy. I think we should stop here by yes. Let's start with the what is simulation. We have known what is simulation. So let's see the simulation procedure. The simulation program begins by reading input data. Initialize the reservoir that comes to the 0 point of the reservoir. Then this part will not change as a function of time. I mean that every time you run the program, you have to have initialization. So well and field control data are then must be read. It reads the information about the well and the field. After that, the coefficient of the flow equations and the primary unknown variables are then calculated. This is in the beginning. What comes later? This is a diagram showing you the simulation procedure. As you can see on the left side of the diagram, the start, and on the right side is the end. What comes start is read input data, initialize, then read rates of the field and of the wells, calculate flow coefficients, and then solve node unknown. If you have any unknown node in the data, or you cannot give him this node position or parameters of the node, then he will start solve it. Then update physical properties and create output files. But in between the read rates and the update physical properties, there are two ways of solution. This is the implicit method. In the case of after reading the rates, it will use implicit methods. Oh, and then calculate the flow coefficient. Then go back to the node, go on or to the solve the node unknown. In this case, since it is unknown, it will come back to calculate the flow coefficient back again by using implicit method. These are methods. I don't want to go into details of these methods because it takes a lot of time. And then goes again. If he finds the program finds that there are some other nodes are unknown, calculate it and go back again to the sorry, come back again to calculate the flow coefficient and continue until it finds all the unknown nodes. Then comes to create the output files. The output files, you can check it by using the any text method, either by note or by text, by window text. And then the simulation ends if everything is well, unless you do any changes on the program, on the input data, on the rates, and so on. Then it will end and comes out with the tell you, hey sir, I am finished and I am done with the simulation. Let's speak about numerical simulator. what is a numerical simulator? It's a mathematical model, a numerical model, and a reservoir model. There are three models within the numerical simulator. A mathematical model is a set of PDEs with initial boundary conditions to represent the physics of fluid flow dynamics in reservoirs. These differential equations do not have analytical solution only in the very simple case. Then the numerical model, the reservoir is discretized into three-dimensional grid blocks alongside with the time allows the PDEs to be solved numerically. PDEs is and this is the known factors of the wells and of the operations going down there. Then you have a reservoir simulator. Computers are needed to solve these numerical models leads to what is called as reservoir simulators. So as I said, numerical simulator contains mathematical model and a numerical model. These mathematical and numerical models will lead to the reservoir simulator. Mathematical model that collects all the available data, that's for a static model. Join them together in order to understand what kind of reservoir you are having and what is the dimensions of the reservoir, what is the number of cells you have in this reservoir. Then you have a numerical modeling. This is in case collect all these information together and show you the 3D grid blocks alongside with the time and allowing time. With time allows the PD to be solved numerically. What is a numerical simulator? Again, it is a mathematical model which accounts for physical, chemical, and thermal behavior of multi-phase fluid flow in the complex geology found in the reservoir. As you may see that from this photograph of the one reservoir, this is the mathematical model of the reservoir showing you the concentration or saturation of for example, here water in the reservoir after depletion, and show you the wells that were drilled in this reservoir, and you can see the blue one. Okay, down there, the scale of saturation. Lowest saturation is the blue one, which is on the left side of the grid. It doesn't show any show very clear what's the number of saturation, but after all, then you have higher concentration on the blue one. This is the top. Then the less and less and less saturation. Why numerical simulation model? It is desirable to forecast the future under various production mechanisms before deciding on a development plan and investment strategy. It can show you the future forecast of the field and the under consideration or under study. Then it is necessary to develop techniques to simulate, assume the appearance of the reservoir behavior under likely production schemes. You can, of course, you can go through the simulation and see the progress of the production and the saturation of each fluid during the simulation time that's of the reservoir. So it is desirable to constitute the reality of the reservoir into our model. That's radial model, actually. It's better to use the radial model. Field can be produced only once, whereas the model can be used repeatedly to evaluate reservoir behavior under different depletion mechanisms and constraints. Also, you can have here the simulation can be done only in the case that it can be used repeatedly. So you can use it several times by changing the factors and the of the reservoir, the numerical model of the water zone, and so on. So in order that to see what the changes of the saturations all over the life of the field or the reservoir. Benefits of reservoir simulation. What we get, what are the benefits of the reservoir simulation? It gives you the accurate determination of reserves, prediction of production performance, determination of number of wells needed, determination of the best well pattern, and the determination of the best perforation interval. Simulator can show you, can give you all these information, where to perforate, where to put a well, where the number of wells needed, and the production performance of each well and the reservoir, the accurate determination of reserves. So anyway, you can use this, of course, the simulation for to solve you so many and save you time in order to get the best of the simulation, the best of the simulator and the best of your operation, and the number of cases you may do, so many sensitivity cases to see the changes, which is the best. Sometimes you choose to make similar. For example, you expect that maybe water injection is better. You put the injection wells, see what is the progress of the saturation of hydrocarbon in the reservoir. Sometimes you expect to use ESPs, electric submersible pumps, use the gas injection in the gas cap or in the oil zone. All these can be done repeatedly, so you can see the changes of the saturation during the life of the field. Benefit also we have here, the simulation will assessment of the early gas or water breakthrough and investigate how to minimize it. A determination of the best injection rates and the best time for injection. Confirm understanding of reservoir flow barriers to assess whether non-drained regions exist. Estimate the optimum time for new phases. All these are also benefits from the simulator. We have seen, we have so many types of simulators in the produced by the companies, and simulators exist, different types of simulators corresponding to different mathematical models. Sometimes, well, these simulators are black oil simulator, the basic equations of water, oil, gas, plus fluid properties tables as a function of pressure. The compositional simulator, the basic equations by component, plus fluid properties as in equation of state. Dual porosity, you may have dual porosity or dual permeability simulate in the field, so you can use dual porosity and dual permeability simulator. Basic equations of matrix and fractures plus terms of changing between fracture and matrix. Thermal simulator, which is specialized for thermal simulation for thermal processes, which uses basic equations of water, oil, and gas, plus equations of a state of conservation of energy. Options of commercial simulators. There are several simulators. We have Eclipse, or Eclipse produced by GeoQuest Schlumberger. Agreement on free use of black oil, compositional, thermal, and front sim models for education and research purposes. So Eclipse contains all these types of simulators, which is black oil, compositional, thermal, and front sim. Fee charged for company-funded projects. Of course, the company uses this simulator have to pay fees for using this simulator. VIP Landmark, which is produced by Halliburton. Agreement on fee use of black oil and compositional models. They implement fees on using if you use the landmark for black oil and compositional models, you have to pay some fees. CMG, sorry, sorry. CMG, Computer Modeling Group Limited, low annual fee for university programs, so it's better for studies and for universities that's cheaper than others, than Eclipse and VIP. They have affordable or for small oil and gas producers. So it is also used, can be used for small companies because it is cheaper than others. These are the differences between black oil and compositional models. This diagram show you the differences. For example, here we take a black oil. This is for volatile oil represented by two components, gas and oil plus solution gas. Sorry, sorry. The compositional model, volatile oil is represented by number NC, number of components. So each component, like for example, you have Y and X, different fluids. This is vapor. For example, Y is used usually for vapor part of the oil, and L is used for liquid part of the XI, used for the liquid part of the oil. Of course, each component, each one of them, the vapor includes 1, 2, 3 until n number of components, and the X, the liquid part, contains also a number of several components. That's how these that's how these models deal with the volatile oil in the reservoir, either the black oil or the compositional. If you are doing a reservoir simulation study, These are the steps that should be taken by you in order to decide, in order to do a study. First of all, your problem definition, data review and data acquisition, selection of approach. How do you approach how to solve this problem, or reservoir description and model design, programming support, history matching, uh, prediction, editing and analysis reporting. These are the main steps in simulation reservoir study you should follow in order to solve your to make full a full description, a full study of the reservoir. Integrated reservoir model. Integrated reservoir model combines several models of several information. The essential elements of the integrated reservoir model is integration of people, data, technology, and tools, multidisciplinary team of geophysicists, geologists, petrophysicists, and engineers, objectives, and the process independent of individual disciplines. This means that the integration includes include all these information, and the information comes from the all these team, these team members, and join together in order to arrive to an integrated reservoir model. Reservoir characterization. Let's take this is the very important part of the study. You have here a task. You have a structure, facies, petrology, diagenesis, geochemistry, and petrophysics. To each one, there is a special person working for it. For example, for a structure, we have a structural geologist and geophysicist. For facies, we have sedimentologist, seismic, sequence, and stratigrapher. For others, we have petrologist, petrophysicist, and geochemist. And for each stage, you have a product. For example, the structure, structure maps and layers, reservoir surfaces, faults, plane maps, reservoir limits. And for facies, you have the positional model and reservoir limits. For others, petrology diagenesis, we have pore system properties and rock fluid interaction. Of course, the simulation study or simulation overall contains two parts, consists of two parts. You have a static model and dynamic model. What is the static model? Which is the model of reservoir at time of discovery. There are several tasks that should be taken in order to construct the static model, but these tasks should be done by a certain specialist. For example, we have fluid properties and saturations. This is done by reservoir engineers. And the product is the static engineering properties. Geologists, petrophysicists do the flow units in order to define layers with similar flow properties. Geologists and engineers, deterministic versus stochastic models. They agree whether the model is representative of the reservoir or not, depending on the input data and depending on the deterministic and stochastic model. We have 3D distribution of properties. We have geologists, engineer to do the 3D distribution of properties, which results of volume model of reservoir properties. Excuse me for a minute. Then, after constructing the static model, we go to the dynamic model, which is the simulator work on this one more than the. It takes the, of course, on both of them. It needs both of them, static and dynamic model. But if you have a very accurate static model, then the dynamic model will work perfect. So what is the dynamic model? Dynamic model includes also several tasks to be done. For example, upscaling a simulation model. This is geologist and engineer. Do this to adjust to reservoir simulator scale. You have geologist and engineer also. Calibrate model of wells, facilities, the expected, for example, the model will give you the volume of hydrocarbon you have down there. So you have to calibrate and see, according to your calculation, mathematical handmade calculation, you have, for example, a certain volume of hydrocarbon, but it is different than the one calculated by the software. Then you have to check again and see. But usually a 10% difference is acceptable in any because there are several factors that may produce this difference between the calculated handmade calculation and the software calculation of the volume of hydrocarbon. Then, if you have a history match, then you have to check back again, see where is the what are the changes that make what are the information fed to the software that made this difference, and you don't have any match between the calculated and input data. You have history match, that you can have pressure matching and production matching. You should have, but you have to check that. But also 10% change is acceptable in any study. Then the engineer do the forecasting and optimization, which makes optimum reservoir development plan. You have several plans, you have several idea, but which one is the optimum? You have to check and see which one is the best and the more economical, which is done by the engineer also by checking the economics and the risk analysis of model and find the economic part or the economic one of these suggestions. Here is reservoir simulation study. You have a problem definition, data review, data acquisition, selection of approach, reservoir description and model design, programming support and history matching. Then you have prediction with operating plans of interest. And the last one, selection of best operating plan, which is the economical one. And we have to have, of course, an economist, and maybe you should have, um, uh, and you have studied or you have the idea of how to do the calculated economic calculation for any suggestion in order to see which is the more economic one. Example applications of reservoir simulation. Determine the performance of an oil reservoir under natural depletion, water injection, or other injection processes, and choose the optimal recovery process. Here, recovery process is also, we can mention the enhanced, the EOR process, which is the best one to be chosen. Determine the effects of well location. What if you change the location of the wells? Do they change the performance or not? Spacing and producing rate on recovery. Here we have some results, example results from the simulator. For in this case, we have gas lift and ESP cases. We compare in between them to see which is the best one in the which is the best one, either the gas lift and the ESP. The results show you the FOE, field oil efficiency, which is the recovery. This one is the top right, top left one. And FPR, this field production rate, show you the field production rate. And the FOPR, field oil production rate. This is FPR, field production rate is the whole fluids, either dissolved gas or compressed gas with oil, water, and so on. But the FOPR is the field oil production rate. FWCT, this is field water cut. Of course, the first letter always refers to the either field or well. We have also other, you can produce for each well the production rate and oil production rate and water cut for each well. Since you change only the F by W, for example, WPR, this means well field production rate, and WOPR, well oil production rate, and WWCT, this is well field water cut. Sorry. This is another example of water injection patterns. We have some changes, some different patterns here. Can show you each one. FOE, FPR, FOPR, FWCT of each one, of each pattern. Here we used the 5-spot and we used 7-spot production in order to see which is the best one that gives us the best results. And this are the results of gas injection and water injection in each case. So it will it can show you also the efficiency or field efficiency and field production rate and field water cut. So in order that you can decide which is the better one. Of course, after collecting all these 3 examples, we should see the best one economically and technically. This is the most important one, technical one, and the economical part of the simulation or of each case. Now we come to the which EOR method is required. I think this is an answer to a question yesterday by by one of the attendants. That's how to choose which is the best one. Now we will answer your question, and maybe it is the question of most of you. In order to choose the suitable EOR method, we need to know the reservoir properties and characteristics, productivity of the reservoir, performance, and fluid saturation. Residual fluid properties and characteristics. like the density, viscosity, and compressibility. Here, what is important in this information is the productivity and performance. If you have the performance is degrading down and your field seems that or reservoir seems that it's going to die, and if you didn't recover much more hydrocarbon from it and you need to recover more, then you should decide which EOR method you should choose. Here comes the answer. EOR decision. Decision of implementing EOR or not depends on such results. The results we have seen before. If the field performance is getting worse, we should implement an EOR method. The type of the EOR method can be decided applying the screening tables. There are screening tables. We will come through it in the next slides, which will give you an idea of how to choose the suitable one for your reservoir. A pilot test should be implemented on part of the EOR method. You should do a pilot test on part of the field or the reservoir and see what are the results. Are they suitable for your case? Are they economical? Are they technically possible? And then decide. If not, then you have to change to another process of EOR. If the field performance is not improving, then we should implement another method. This is the decision that should be taken first. If not proper, then you should change to another method. This decision should be taken suggested by you as a reservoir engineer and give your reasons for why not or for choosing such a method than the other, but have to be improved or have to be approved, actually approved by the higher management to decide which one is the best, either the one you suggested or you should go and look for another one. Let's see. Screening criteria for EOR methods. You have here the method on the left side, gas injection method, for example. You have water floods, hydrocarbon, nitrogen, flue gas, carbon dioxide, surfactant. Which one is the best? Which one fit to your reservoir? And which one fit to the oil properties that you have? These are the limitations of the oil properties. You see here gravity, viscosity, composition, oil saturation. Then, for example, for water flood, you have viscosity, gravity greater than 25 API, and viscosity less than 30 centipoise. Composition doesn't matter, not compatible. Oil saturation should be greater than 10% mobile. For nitrogen and flue gas, for example, should be gravity should be greater than 24 degree, but for gas, for nitrogen, you should have more than 35 degree. Viscosity should be less than 10 centipoise, and you should have the composition high percent of C1 to C7. Oil saturation should be greater than 30% for volume. Then you can decide which method. Let's go to another table. We have chemical flooding and thermal with the in comparison with the oil properties, available oil properties of your field, you can choose which one, polymer or alkaline for the chemical flooding. For the thermal, you can choose in between combustion and steam flooding, depending on the oil properties of your oil, which supposed to match with one of these processes. Here comes the, again, gas injection method. What are the reservoir characteristics? Formation type, net thickness, average permeability, depth, and temperature. For example, for water flood, sandstone, or carbonate, you have net thickness is not compatible or not required. No, it doesn't matter. All doesn't matter. You can use it anytime for any type or any thickness, any permeability, any depth, and any temperature of the reservoir. But for example, for nitrogen and flue gas, if you have sandstone or carbonate, then net thickness thin and less dipping. Average permeability not required, not compatible. Depth for greater than 4,500 feet. The temperature is not compatible also. But for example, surfactant polymer, sandstone preferred. Net thickness should be greater than 10 feet. And the permeability should be more than 20 millidarcy. Depth less than 8,000 feet. And the temperature is less than 175 degrees. So for each method or each process, you have different reservoir characteristics, and also these characteristics should match with the one that you have or the match with your reservoir. Also here we have chemical flooding, polymer alkaline, sandstone type of formation preferred, carbonate possible, net thickness not compatible, average permeability greater than 10 millidarcy, depth less than 9,000 feet, and temperature is less than 200 degrees. So on for these for the thermal operation also. So I think I have done what is required in the short time we have, and you can decide which one you should choose, which process you should implement. But after all, there are more details have to be looked after, and this can be found in so many books about the textbooks or researches about EOR for which method, which simulation, how to do the simulation, how to do the choice, and how to do the screening of the EOR method. There are several books that deal with this these categories, so you can go and look for it. It is available also on internet, so you can find these books. So I think I'm done. And do you have any question?